All right. So in the last class, we were discussing about the line of sight path following control for a marine craft, where we were using this idea of successive loop closure, where the idea was that we were having a control system which was trying to control the heading of the vehicle given to a desired heading angle. And then we were trying to close an outside loop of it where the guidance system was taking in the positions in order to provide the desired heading angle for the craft using the line of sight algorithm. We also introduced the idea that we want to introduce the integral line of sight approach because there might be unmodeled dynamics in terms of the crab angle, which we are not considering in the line of sight. So therefore, it makes sense to include it in the integral line of sight scheme. When we do that, we are going to take care of it using this term ki times yp int, where yp int's dynamics is given by this. This is chosen such that the system exhibits a uniformly semi-exponentially global situation or a global stability, so that it promises us certain characteristics in terms of robustness. And the idea here was that if you wanted to look at the waypoint switching mechanism, we typically will see that when the craft is within certain radius of a particular waypoint, we start tracking that waypoint. When the craft enters a certain region inside the circle of a second waypoint, it shifts from the first waypoint to the next waypoint, so on and so forth. That is just one methodology, but we also saw a few others when we were discussing the guidance systems, which could be used for this purpose. The only thing which is left for us today is to cover the dynamic positioning system. So far we have looked at the idea where the crafts were moving with a forward speed and trying to attack a path following problem. But if you want to look at it from a dynamic positioning point of view, how does the controller work? And again, the methodology is no different. We'll use the same methods which we have developed so far. We'll use the MIMO PID controller for this particular case. The only thing is the dynamics will be slightly different. Just give me 1 second. All right. Okay. So what we are going to take a last look at in terms of the control system would be to look at, for a dynamic positioning system, how does the dynamics look like? Because we know that in this case, we have a bias term which is trying to account for these environmental disturbances. How do we take care of that? So nothing new per se, but at least the dynamics looks slightly different, but although it's exactly the similar format as what we have seen before. So our equations of motion are the same as what we saw before. We have the kinematics, and here we are going to consider a 3 degree of freedom system, okay, which means we are looking at a surge, we are looking at sway, and we are looking at yaw. Okay, so that is why you see that instead of that J matrix which comes in here, we have the rotation matrix specified, because that's only taking care of the rotation in 1 degree of freedom, which is the yaw angle. So we are not considering pitch and roll in this particular scenario. Our equations of motion are given by the mass times the velocity, the acceleration vector plus the damping times the velocity vector is equal to some rotation matrix transpose times B, where B is this bias vector. And we have seen this before when we formulated the system equations for the dynamic positioning system, where this B is taking care of all the slowly varying drift forces that we are going to experience. And we are kind of modeling them in a in a simplified manner, you might ask, that we are specifying that the wind, wave, ocean currents, and unmodeled dynamics are kind of all clubbed together in this bias term. It's not a very accurate model, but it will get the job done with respect to the ship dynamic positioning systems, because we will have integral component in our controller to compensate for these dynamic effects, take care of it. So for now, we don't care so much about accurately modeling them because we are not doing a feed forward control system here, but rather we are trying to compensate for them using the integrator. So therefore, we are not so worried about the dynamics being captured properly. So we have the rotation transpose matrix multiplied by the bias term plus the control thrust, which is which is coming from the controller. And then you have the wind and the wave. Okay, so basically this bias term is accounting for unmodeled dynamics. So if I want to write it down, it's looking at unmodeled dynamics plus ocean current effects. Okay. All right, and we can kind of model that as a slowly varying system by specifying B dot is actually going to be 0, which means B is going to be more or less constant. Here we are assuming that the disturbance is constant in the NED frame, which means we are assuming that over the small region of time that I am observing, the environment is kind of steady in the sense that environment is not changing in the NED frame, but it is changing with respect to the body fixed frame because the ship is moving itself. Okay, because the ship will be weather vaning and doing things of its own. So the environmental forces will act in one direction. That is what is being presumed. Okay, notice one thing here that when I wrote down this rotation matrix R of t, it's not specifically varying with time, right? It's the yaw angle which is varying with time, which is implicitly giving a dependence on the time for that rotation matrix. So the idea here is that I precisely know psi is what I am saying. So that rotation matrix is not an unknown quantity for me, but I actually know the value of psi from some measurements, either from a compass measurements or from a gyroscope measurements. I'm able to precisely get the estimates of psi so that I can precisely get what this rotation matrix looks like. All right. Again, as I said, these ocean currents are modeled by this bias term and are assumed to be constant in the NED frame. So when we now start to look at this system and we want to control that, so we want to have a controller which can specify that if I want a desired path, how do I ensure that the desired path is followed or a desired set point is followed? Then we go ahead and we will specify it in terms of our typical PID controller. The only difference being here is that we have to worry about what are the effects of the waves and what are the effects of the ocean currents and the wind separately. One of the effects of the wave is waves will introduce a first order motions in the system, which we do not want to compensate for. They are oscillatory motions which we don't want to compensate for. Because if we try to start compensating for them, one, we may not be able to because the time period may be very, very quick. Okay, because they will be responding at the wave frequencies, which will be order of seconds. And we are not quite sure that our thrusters can be capable of applying a thrust which will allow it to compensate for these forces in a matter of seconds. So rather than wear out our actuators, it is much better to rather only compensate for the slowly varying drift forces. So we want to kind of isolate that slowly varying drift forces and estimate them. So when I get the total motion of the vessel, I want to be able to eliminate what is the first order motion and only focus on what is that second order motion which is happening. Based on that, my controller should take an action. Is everybody with me? We want to take the action only based on that slowly varying component of that motion. We don't want to take action based on the first order component. So we will need some sort of a state estimation or a filter where whatever we are measuring, let us say our sensors are measuring the motions, we need to filter out that motions and remove whatever is the wave frequency component from it, and then we only be applying our control logic basically to the low frequency stuff. So filtered motion only should pass through our feedback. the actual first order wave disturbance should not pass through our feedback. So therefore, the state estimator will play a significant role in terms of a DP control system, where it has to figure out what the states are, and also it has to filter out the first order wave observations in order to give me the second order wave observations, which can then be fed into my control. Now, we'll discuss about state estimators at length in the next class onwards when we start talking about navigation systems, and we'll spend some considerable amount of time on that. But for now, just understand that there is a need for the state estimators to be very robust for our dynamic positioning systems to work properly. Okay, some of the components which we should definitely include when we are looking at this dynamic positioning systems would be that we should have an integral action so that we can compensate for these slowly varying drift forces. Then we should have a wind feed forward control to compensate for the mean wind forces. We should have a wave filtering, which should remove the first order wave induced oscillations and only feed that second order slowly varying oscillations into our feedback loop. So our feedback should only be based on these slowly varying stuff. And then we should have a state estimator which can filter out this noise and can estimate the unmeasured states in a precise manner. And for this, we'll typically be using the Kalman filters. Finally, the last component of your, which you should have in your commercial heavily available DP systems would be an optimal thrust allocation system, which means that given that I want a certain amount of thrust to be generated, what is the set points for the different motors? So let us say that if I have a bow thruster, at what RPM should I be running my bow thruster? If I have a rudder, what rudder angle should I be positioning in order to get the required thrust which I need to keep my vehicle in place? So if I see the block diagram for the system, you will see that it kind of looks slightly differently as compared to your regular system, in the sense that we have our first order disturbances coming and getting added to our plant dynamics, assuming that our plant is only representing the slowly varying stuff. Okay, and once we have those two being added up, the measurement is happening with respect to either a GPS system or a compass system, which gives me the position and the heading of the vehicle. Now we take this position and heading and pass them through a Kalman filter and a low pass frequency filter, so that we can filter out the high frequency stuff and we are left with the low frequency signal at the end of it, which we then feed into our control system here. And our control system takes an action based on that, which then will try to compensate for all the drift which is happening in the system. Okay. The only difference here is that we have to make sure that this observer for plus filter becomes particularly important to remove this guy. We don't want to consider that fellow. And we'll discuss about this at length when we start discussing about the navigation systems. Okay, so coming back to the idea of the controller, we can see that we are going to follow the same approach as we had seen before, using the MIMO-based nonlinear PID control technique, where the total control law will be a feed-forward term used for the wind. So we are estimating the generalized wind forces and opposing it based on wind measurements. And then we have the other part, which is the rotation matrix transpose times the PID controller. Again, you'll notice that this thing is R here instead of J, because we are looking at a 3 degree of freedom system. So when we looked at the generalized control law, we had the J matrix there, which gets reduced to the R matrix when we are looking at a 3 degree of freedom system. Is everybody with me so far?
Yes, sir.
All right. Okay, so our PID law is again given in a similar fashion as before. We have the KP matrix times the error term and KD matrix times the derivative in velocity and KI matrix times the integral of the error. If I plug this PID control law into this term here, you'll see that the total control law is given by this, where we have the wind feed forward, proportional term, derivative term, and the integral term. And I can represent this so-called matrix which you see here, R transpose KD times R, as KD star. Typically, what will happen is we'll choose this KD matrix to be a diagonal matrix. So what is happening? We are doing R transpose times some diagonal matrix times R. It is equivalent to as if I am just multiplying R transpose R will give me identity, and what I'll be left with is still the same diagonal matrix as before. So I can kind of approximate this, not approximate, it actually will be exactly equal to KD. So KD star will be equal to KD if KD is a diagonal matrix. Whereas when K is not a diagonal matrix, KD is not a diagonal matrix, I can't say the same. At that time, KD star will be time varying. Okay. For most practical applications, we'll always be choosing diagonal matrices for our systems, which we'll be based on our pole placement algorithms. So therefore, it should be taking care of itself. All right. Asymptotic stability for the system follows from Lyapunov arguments. We have seen this before. This is the same idea which we have seen for the NEMO-based nonlinear PID control law. So whatever holds there continues to hold here as well. Only the idea here is that we will need for a practical implementation, we need the state estimator and a wave filter will really be important in a dynamic positioning system, which the wave filtering was not really needed for our other aspects, but they'll be particularly needed in the DP system where I only want to compensate for slowly varying drift forces. We have seen what this wind feed forward, estimated wind feed forward thrust looks like, and I'm kind of just summarizing everything here. We have already taken a look at this dynamics before, which will be given by half times rho A times VRW, where VRW is the relative wind velocity. And then we have the coefficients Cx, Cy, and Cn, and the projected areas, the frontal projected area, the lateral projected area, and for the yaw, you will have the lateral projected area multiplied by the length overall of the vessel. Okay. And we had even seen at some of the representative numbers for these coefficients and how they vary actually with the relative heading angle, which is gamma RW. So we had taken a look at that in the modeling section. So we are just summarizing that here. So it is just putting together as to how we will estimate these wind forces. VRW here was nothing but square root of URW square plus VRW square root of that. Actually, there is no square root. If there is a square root, then this should not be there. So that's a mistake in the notes. Please mind that. Okay, and the relative angle is A tan inverse VRW and divided by URW, where URW and VRW are the relative velocities of the wind with respect to the craft's velocity. So you have the body fixed frame's velocity minus the wind velocity in the longitudinal direction of the ship, and similarly you have the sway velocity minus the velocity of the wind in towards the lateral direction of the vessel, and they can be expressed in terms of VW and beta VW. So basically what happens is we are measuring VW and beta VW, so wind speed and wind direction. Based on that, we can compute all of these quantities here, plug them in to compute these values, and then use them to compute the estimated wind force. That is how we are basically estimating the wind forces from the system. And once this wind feed forward is present, we can plug it back into our controller, and all we have to do is now tune our gains in order to make sure that it goes to wherever we want it to go. We can use the same approach of pole placement method as before, which we had seen for the NEMO-based controller. Okay. So that kind of completes our idea of what is going on. One important thing to note, we want to make sure that these wind measurements should be low pass filter, because we don't want to compensate for very high frequency stuff, because our actuators probably cannot do that because the inertia of these systems is really, really large. Again, feed forward is a better approach to go rather than a feedback through the controller, especially the integrator, because the response time is much faster when I try to do a feed forward compensation for the wind rather than rely on my integrator to compensate for the wind. Okay. And those aspects we have already seen before and discussed before. So it kind of brings to a conclusion of how we would design control systems, whether it be for path following or whether it be for dynamic positioning applications. How can we design heading controllers and close the loop further using our guidance systems is what we have kind of looked at in this overall picture. Now, there are times when you want to kind of move away from the PID system and try to move it and look at different controllers like the nonlinear controllers. And some of the typically popular nonlinear controllers would be LQR, which is linear quadratic regulator, or you could be having a backstepping controller, which is basically trying to find a control law using the Lyapunov theory such that the controller is going to be stable enough. Or you could have a sliding mode control where we are going to say that I don't care about the current dynamics of the system, but I'm going to force it to follow a certain dynamics where things are well mannered. But the problem with all of these different nonlinear controllers is that they are a little more harder to implement, computationally a little more expensive. Also, another topic here which I kind of forgot was MPC. Okay, this is called model predictive control, which means that you have a model of the plant and you're trying to simulate different control aspects. What happens when I try to project it forward into some time and see how the system behaves. Based on that, I figure out how to optimize and take the proper action. So they are all based on some nonlinear methodologies and are going to be computationally a little bit more expensive. Okay, but they may be needed because we may be having a hard time tuning our gains in some problems, in which case we will typically make use of them. But for most practical applications, we will typically see that PID controllers are what are generally used, especially if you want to do some set point tracking and things like that. But if you want to do some adaptive things and which should be able to adapt to different environments and should be able to handle complex dynamics of the system, that is where you typically need these nonlinear controllers. And that is why those theories have been developed. But they take more time. The real-time implementation is becoming more challenging as you add computational effort to it. Okay, so that's the overall summary of what we discussed in motion control systems for a vehicle. And maybe we will stop right here, and the next lecture onwards we will try to continue forward where we'll discuss about model-based navigation systems, where we'll discuss about we'll spend most of our time on what you call fixed gain observers. And then we'll spend some time on Kalman filters. And you'll see that both of these are actually applicable to linear systems, but there is some possible extension which we can do, which is called extended Kalman filter, where it can deal with nonlinear systems as well. Okay, so we'll try to understand when can a system be deployed with a Kalman filter, what are the necessary conditions, what is meant by observability, what are fixed gain observers, and we'll discuss about Kalman filters a little bit. Okay, so that's all for today. Are there any questions before we close now? Yes.
Sir, I have a general doubt.
Yeah.
Do these aeroplanes and rockets, do they use PID controllers or something like these nonlinear controllers?
They probably will require some nonlinear controllers because things will not be as well behaved. For some aspects, they may be using PID controllers, but it really depends on the application which they are using for. Okay. So let us say that you have an aircraft where you're looking at a commercial airline, okay, and commercial airlines autopilot. There, things may be well mannered. You can probably get away with PID controllers for most of the time. Okay, but if you're doing flying acrobatics with a fighter jets, then you probably will not be able to achieve all that you want to achieve using PID controllers. So that's where you might want to have more stronger nonlinear controllers which allow for the stability of the system to be prescribed in a proper manner. Okay, so we have both these tools on hand. We have to choose as a control engineer, depending on the problem statement, which might be the more suitable tool for depending on the type of the problem that you want to apply to it. For most of our marine controllers, because things are much slower in nature, the inertias of the system are much larger in nature, you'll see that PID is ubiquitously used in marine systems. Okay, you don't see you do see some amount of LQR systems being used as well, but you won't really see a lot of SMC and backstripping controllers being very popular in the field. Most of the times PID can get the job done. Where PID is unable to get the job done, there you'll have to work with these things. Now with the latest motivation of autonomous ships where you want to include obstacle avoidance and things like that, there too you will see some more complex controllers coming into the picture, which can not only handle the fact that you are only trying to drive your error to zero, but you want to avoid some obstacles in an effective manner. So some adaptiveness is required. There too you will see some of these other controllers playing a more significant role. Okay. Any other queries? In that case, let me stop recording here.